Hi everyone. The plan for today is to discuss deep convolutional neural networks. We will discuss their structures and look at some important applications. To be able to discuss convolutional neural networks, we need to know what convolution is. The convolution is an operator that takes two functions f and g and creates a new function. This new function is denoted by f star g. The value of this f star g function at location t is defined by this integral here. We integrate f tau times g t minus tau with respect to tau on the whole domain. You can also prove that this integral is exactly the same as integrating f t minus tau times g tau with respect to tau. I'm visualizing this convolutional operator for two one-dimensional functions here. The blue curve is function f tau, the red curve is function g t minus tau, and as you can see, as we change the value of t, this function shifts from left to right. The yellow region is the area under f tau times g t minus tau, which is the same as the convolution of f and g. This resulting function of the convolution of f and g is visualized with this black curve. Here we can see if we convolve the density of two uniform distributions, then we get the density of this triangular shape. As a special case, we can also consider functions whose domains are not the whole real line, but instead they have discrete supports. For example, the set of integers. In this case, everything is the same as before, except the integral becomes a discrete sum. As a special case of this, we can also consider functions whose domains are finite discrete sets. For example, here the support is -m plus 1, and so on, m minus 1, m, discrete integers. When the support of the functions are finite and discrete sets, then we can think of those functions as vectors, finite dimensional vectors, and we say we convolve two vectors. This is how we can define one-dimensional convolutions. When we convolve two functions, f and g, the function that has the smallest support is often called the kernel of the convolution. Convolutions might look quite abstract at first, but I'm sure you already use them in practice. For example, if you want to multiply two polynomials, then in practice you calculate a convolution between two vectors. In this example, I want to multiply x plus 2 with 3x squared plus 2x plus 5. I can collect the coefficients of these polynomials into two vectors. The coefficients of 3x squared plus 2x plus 5 are 3, 2, and 5. And the coefficients of x plus 2 are 1 and 2. If we use the previous definitions of convolutions between two vectors, and we convolve these two vectors, then we get this third vector, 3, 8, 9, and 10, which are the coefficients of polynomial 3x to the 3 plus 8 times x squared plus 9x plus 10, which is exactly x plus 2 multiplied by 3x squared plus 2x plus 5. So multiplying polynomials can be calculated with convolutions. This is how we defined the one-dimensional convolutions. If f and G were two vectors, then the definition of the one-dimensional convolution was this expression. When f and g are two functions, then this sum becomes an integral. We can generalize this concept to multidimensional vectors and functions, and then we call that convolution multidimensional convolution. For example, let f and g be two matrices, then the convolution of f and g matrices is another matrix, and the value of that matrix at location n1, n2 is defined by this expression. If f and g were functions with multidimensional domains, then the convolution would be defined with multidimensional integrals. Similarly, we could generalize convolutions to even higher dimensions, and then, for example, instead of matrices, we could consider using tensors as well, and then we could define convolutions between multidimensional tensors. Convolutions are often used to filter images. For example, let's use this RGB image here. The red, green, and blue channels of this image can be considered as two-dimensional matrices. Consider also this 5 by 5 matrix here. You can easily check that if we convolve each channel of this image with this 5 by 5 matrix, which is called the filter or the kernel of the convolution, then the convolved image will look like this edge-detected image here. The reason for this is that at each location, this convolution calculates 8 times the pixel value in that location, minus 2 times the left, 2 times the right, 2 times the top, and 2 times the bottom pixel values. If these nearby pixel values are very different, that is, the pixel values change by a large quantity locally, then it means that there's an edge there. If we choose a different filter, for example, this one that contains only the same 0.04 values, then this convolution calculates at each location the average of nearby pixel values. As a result, this convolution blurs the image. So, depending on the convolutional kernel, you can get very different filtering effects. The convolutional neural networks will use convolutional filters, and the kernels of these convolutions will be the parameters of the neural networks. Now that we know what the convolution is, we can define the convolutional layer in neural networks. In the multilayer perceptron, the layers are very simple. An input X was multiplied by a matrix W, and then we applied a nonlinear activation function F on this result, and this was the output of this layer. The convolutional layer is very similar, but instead of using a matrix multiplication, the input X is convolved with the convolutional kernel W, and then we apply a nonlinear activation function on the result of this. Here you can see the convolution in practice. Let the convolutional kernel W be a 2 by 2 matrix. For a given input matrix X, this is how we calculate the output matrix Y, that is the result of the convolution. The top left kernel, Y00, will be simply X00 times W00 plus X01 times W01 plus X10 times W10 plus X11 times W11. That is, we multiply this element with this element and then add the product of this element with this element, and the product of this element with this element, and then the product of this element with this element, and this sum will be the result of the convolution. The value next to it, that is y01, will be x01 times w00 plus x02 times w01 plus x11 times w10 plus x12 times w11. So we just need to multiply the appropriate input matrix values with the corresponding kernel matrix values and then add these quantities. After we calculated this convolution, in the convolutional layer, often we also apply a nonlinear activation function on the results of the convolution. In this case, the input matrix has size 6 by 6 and the output matrix is 5 by 5. Without the bias term, a fully connected layer would have 6 times 6 times 5 times 5 different parameters to train. As you can see, the convolutional kernel in this case has only 2 times 2, that is 4 parameters to train only. So compared to standard fully connected feed-forward neural networks, CNNs have much fewer connections and parameters, and because of that, they are easier to train. There are some other important neural network layers that are often used in convolutional neural nets. We will discuss them now. We often use pooling layers in convolutional neural networks. There are two different types of pooling layers. One of them is called max pooling, the other is called average pooling. Given a matrix or tensor input, these pooling layers create a smaller output matrix or tensor. As you can see here, the input matrix has size 4 times 4, and then we created 2 by 2 output matrices. I will illustrate the max and average pooling on this example. The pooling layer selects several submatrices of the original matrix. In this case, we chose 4 different submatrices. They are colored with blue, orange, green, and red colors. Here, each submatrix has a size 2 by 2, but this is a hyperparameter, and you could choose anything. In this case, we chose the stride parameter to be 2, but you could also choose any positive integers. This stride parameter determines how to select these submatrices. So first we select the top left 2 by 2 matrix, and then we move stride parameter number of steps to the right, and then select the next submatrix. In this case, the stride parameter was 2, so we moved 2 steps to the right. Once we are done with selecting submatrices in this top row, we move stride parameter number of steps down and select submatrices in the next row. Since the stride parameter was 2 in this example, we moved 2 steps down and selected this green submatrix. And then again we move 2 steps to the right and select the next submatrix. We do these steps till we select all the submatrices. In this case, these submatrices are not overlapping since each submatrix has a size 2 by 2 and the stride parameter was set to 2 as well. However, if you set the stride parameter to say 1 only, then the submatrices would be overlapping. When we are done with selecting all the submatrices, then the max pooling calculates the maximum of each submatrix and creates a new matrix of these numbers. So for example, the maximum of the blue submatrix is 12, and therefore this element of the new matrix will be 12 as well. The average pooling works similarly, but instead of calculating the maximum of the submatrices, we calculate the average value of the submatrices. For example, this blue submatrix has values 8, 7, 12, and 9, and the average of these is 9, so this element of this new matrix will be 9 as well. Another important layer that we often use in classification problems is the softmax layer. Often, this is used as the last layer of the neural network. It can convert any real-valued vector output to class probabilities. Imagine that we have capital K classes, and for a given input, the neural network produces a capital K dimensional output vector, here denoted by Z1, Z2, and so on, Zk. The softmax layer or softmax activation function is just this transformation here. As you can see, this transformation produces a capital K dimensional non-negative vector, and the sum of these elements of this vector is 1. Therefore, we can think of these elements of this vector as class probabilities. These class probabilities are the final outputs of the neural network. They will go into a loss function, and then we can train the neural network by minimizing that loss function. If you use a deep learning framework such as TensorFlow, Keras, or PyTorch, then it's very easy to use convolutional layers, pooling layers, or softmax layers, because these layers are already implemented in them, and usually it's just a function call to use them. Here you can find some links to the PyTorch documentations of these layers. When you have a chance, please take a look at them. Now we are ready to see how to use these layers and building blocks in deep convolutional neural network applications. The first application we will discuss is the LeNet-5 neural network by Yann LeCun and his coworkers from 1998. This was one of the earliest successful applications of neural networks for character recognition. The neural network gets grayscale images as inputs. Each input image has a size 28 by 28. The goal of the neural network is to classify the input images into one of the 10 different classes. Each class corresponds to a digit from 0 to 9. This neural network has 7 layers. 1, 2, 3, 4, 5, 6, and 7. C1 and C3 are convolutional layers. S2 and S4 are pooling layers, and there are 3 fully connected dense layers, F5, F6, and the output layer. Sometimes the pooling layers are also called as subsample layers. In the next few slides, we will discuss the details of these layers. We will use several 2D convolutions. Here I'm illustrating the two-dimensional convolution on this 28 by 28 input image. First, we extend the input image by 2 constant 0 pixels on each side. This transformation is called padding, so we can say we zero padded the image by 2 pixels. This new zero padded image has a size 32 by 32. After this, we convolve this image with a 5 by 5 convolutional kernel, and this will create a new 28 by 28 dimensional image. We call this new image the feature map of the convolutional kernel. This green 5 by 5 matrix illustrates the convolutional kernel. The top left corner of the convolved image is simply the weighted average of the kernel matrix and the corresponding 5 by 5 submatrix of the input image, that is x00 times w00 plus x01 times w01 plus ... x44 times w44. This 5 by 5 submatrix of the input image, that is the submatrix where the convolutional operator receives its input, is called receptive field of the convolution. After we calculated the top left corner of the convolved image, we moved the convolutional kernel 1 pixel to the right and repeat the same thing. That is, we calculate the weighted average of the corresponding submatrix of the input image, and this will be the next pixel value of the convolved image. We repeat this process till we are done with the first row, and then we move to the next row. And so on. We repeat this whole process till we arrive to the last row, and then finally we calculate the bottom right corner of the convolved image. This is how we can calculate a feature map or a convolved image with the convolutional kernel. Let's continue discussing the LeNet neural network. After the neural network receives a 28 by 28 input image, it goes into the first layer, which is denoted by C1. It's a convolutional layer. It has 6 different convolutional kernels. Each has a size 5 by 5. This blue matrix shows one of them. After we convolve the input image with a 5 by 5 convolutional kernel, it creates a matrix of size 28 by 28 that we call a feature map. We have 6 different convolutional kernels, so we create 6 different feature maps. These feature maps are denoted with C1k, where k is going from 1 to 6. The ijth element of C1k is calculated by this equation. Here we convolve the input matrix X with the k's convolutional kernel wk, then add a bias term bk, and finally we apply the tanh activation function on it. Now let's calculate how many parameters we need to train this convolutional layer. The size of the convolutional layer is 5 by 5. That's 25 parameters. We also have a bias parameter. That's altogether 26 parameters. We, however, have 6 of these feature maps. So altogether, this is 26 times 6, 156 parameters to learn. Let's calculate how many parameters we would have if the neural net were fully connected. The size of the feature maps are 28 times 28. We have 6 of them. And if it's fully connected, then each element of them would be connected to one of the 32 times 32 input parameters plus one bias parameter. That's altogether these many parameters. It is much bigger than 156 that we had when we used a convolutional layer instead of a fully connected layer. We can also calculate the number of connections between the input image and the feature maps when we use a convolutional layer. The size of the feature maps is 28 by 28. We have 6 of them. Each of them is connected to a 5 times 5 submatrix of the input image plus one bias parameter. That's altogether 28 times 28 times 6 times 5 times 5 plus 1, these many connections. This is much smaller than the number of connections in fully connected neural networks. The pooling layer is also known as the subsampling layer. It is denoted by S2 in this picture. So far, we have created 6 feature maps with size 28 by 28. This pooling layer will reduce their size to 14 by 14. So we will create 6 matrices, each with size 14 by 14. These are denoted by S2k, where k is going from 1 to 6. The ijth element of S2k is defined by this equation here. W1k and W2k are two real numbers. They are the parameters of this layer. As you can see from the figure and from this equation, we partition the matrices with size 28 by 28 on layer C1 to 14 by 14 small submatrices, each having size 2 by 2. Then in each of these matrices, we just calculate the sum of the values, multiply it with W1k, add the bias term W2k, and then we apply the tonnage activation function. So this pooling layer just aggregates the information from the previous C1 layer and creates new feature maps with smaller sizes. Let's calculate how many parameters we need to train in this layer. We have 6 feature maps, and for each feature map, we have 2 trainable parameters, W1k and W2k. K is going from 1 to 6. We have 6 feature maps, that's altogether 12 trainable parameters. The next layer, C3, is another convolutional layer. It's very similar to C1 that we already discussed. Again, we will use convolutions with kernel size 5 by 5. Using these convolutions, here we create 16 new feature maps, each having a size 10 by 10. Each of these feature maps receives inputs from several of the other 6 feature maps in the previous S2 layer. For each of these 16 feature maps, this table shows where they get input from, that is, which feature maps out of the 6 maps in the previous layer S2 provide input to the feature maps in C3. For example, the 9th feature map in C3 will get input from feature maps 0, 3, 4, and 5 in S2. We can calculate that C3 has 1516 trainable parameters, which is again much smaller than what fully connected layers would have. The next layer, S4, is another pooling layer. It is very similar to S2. Layer C3 has 16 feature maps with size 10 by 10. This S4 pooling layer creates 16 new feature maps, each having a size 5 by 5. These feature maps are denoted by S4k, where k is going from 1 to 16. Similarly as before, we partition the feature maps of C3 to 2 by 2 blocks, and then we simply add the elements in each block, multiply this with W1k, and then add the bias term W2k, and finally we apply a tonnage activation function on this. The trainable parameters on this layer are W1K and W2K. Since we have 16 feature maps, that's altogether 16 times 2, 32 trainable parameters. We are done with the convolutional and pooling layers in this network. The next layer, F5, is a fully connected layer. It has 120 neurons. Each of them is connected to all the 16 times 5 times 5 neurons on the previous layer S4. Each of them has a bias parameter as well. So this layer has 120 times 16 times 25 plus 1 for the bias parameter, number of trainable parameters. The next layer, F6, is another fully connected layer. This layer has 84 neurons. Each of them is connected to all the 120 neurons in the previous F5 layer. Each of them has a bias parameter as well. So this layer altogether has 84 times 120 plus 1 trainable parameters. The output layer has only 10 neurons. The activations of these neurons are denoted by y hat 1, y hat 2, and so on, y hat 10. Each of them is connected to 84 neurons on the previous layer F6. These trainable connection parameters are denoted by Wij, where I is going from 1 to 10 and j is going from 1 to 84. Here, xj is the j's input from the previous layer F6. The output of the neural network is y hat 1, y hat 2, and so on, y hat 10. They can go into a loss function, and by minimizing that loss function, we can train the neural network. The predicted class label is that where y hat I is the smallest. In other words, if we think W as a matrix, we want to find that row I where this distance is minimal. Let's see some results on the MNIST dataset. The original dataset they used had 60,000 images. They contain some images of digits with size 28 by 28. After training on this dataset, the previously discussed LeNet network achieved a test error less than 1%. To get even better results, they augmented the dataset with 540,000 artificial distortions. They contain some small perturbations of the original images, as you can see here. After training the neural net with this larger dataset, the test error dropped to 0.8%. This is pretty good because it's about the same as human level performance. It's a common trick to augment the dataset with some distorted or noisy images. Here you can see some misclassified examples where the network made some mistakes. I'm showing you the original images, the true labels, and the predicted labels. As you can see, some of them is actually pretty challenging to even us. For example, if you look at this, here the true label was 5, and the network predicted that this image is a 6, and that's also a reasonable guess. Here the true label was 3, the network predicted 8, which is again a pretty reasonable guess. Here I'm showing this LeNet neural network in action. This network is slightly different from what we discussed, but the most important components and layers are the same. These are the input images that the neural network is trying to process. Here I'm visualizing the activations on the layers C1, C3, and S4. The prediction of the neural network is shown here. As you can see, the network works pretty well. Now we study how robust the neural network is if we shift the input images by a small amount. Here, the images are shifting from the top to the bottom, but the network can still recognize the digits correctly. We can also check how robust the network is to small amount of rotations. The rotated images are shown here, and as you can see, the neural network can still predict the labels well. Here we are studying the noise tolerance of the neural network. I'm showing two different noisy input images, and as you can see, the predicted class labels are still correct. Finally, I'm showing some more noisy images with different noise distributions. Interestingly, the neural network, even with this much amount of noise, was still able to correctly predict the class labels of these images 2, 4, 3, and 6. There are many different versions of this LeNet that we discussed, and they are working pretty well. They are robust to some small transformations, they are robust to some small amount of noise, and they are as good as human level performance. Thank you for your attention for now. We will continue with part 2, where we will discuss more complicated convolutional neural networks, and we will see some applications on more challenging data sets.